Bam! Mr. True. In this video, we're going to do a continuation of a video lesson I just posted. I'll have a description below where we showed that these two lines in 3 space that are in vector form are skew. That they're not just parallel and they do not intersect, they're skew and they do not intersect. So they can't intersect, and we have to show that the slopes are different, that they're not scalar multiples of each other. Well, now that that's out of the way, we're going to do another expansion, and we're going to determine line 3 that is perpendicular to line 1 and line 2 and intersects both. So we're going to write the equation of a line. And nice extra bonus through that process is we're also going to find out we're going to determine the closest these two lines come to each other. So they're coming in, they're at a different angle, they're different planes, and there's some closest point that those lines reach, and then they carry on. So we're going to be determining the distance between two lines that do not intersect, which are in 3 space. And I've given away a little bit of an answer here, because the first time I tried to record this lesson, I didn't have my microphone on, so that's exciting. Think back to Algebra 1 and geometry. What do you need to write the equation of a line? You need a point and a slope. Great. How do you determine, let's say, distances? Well, distance between points in space started off with just 2 points. If you want the distance between 2 points, well, obviously, you're going to work out the distance formula. If, however, you want the distance between a point and a line in space, that was a little bit more work, because you can't come in from the given point to the given line at an oblique angle. Then the answer, what's the distance between a point and a line, would have an infinite number of solutions. Just, pick an oblique angle that you want to come at the line towards. No, if you want the distance, if you're asked to find the distance between a point and a line, you have to find the, whoa, chalk down, that was loud. You have to find that perpendicular line segment and then find the distance. So what would that entail? You would have to look at the equation of a line, and step 1, find its slope. Step 2 is you would have to find that perpendicular slope. Then you would have to find, for step 3, the equation of that line. Now, in terms of this, I'm using lowercase letters instead of uppercase letters for my names of lines, but for this particular problem, line sub 3 is going to be the line that's perpendicular to not one of the lines, but both. So that's going to be sort of like line 3. And then in step 4, you would have to find the intersection point between, well, actually step 4 is you have to find the equation of the line. Oh, that was step 3. And then you find the intersection between the new line you've just created and the given line. And you'd find that intersection point, and then finally, now that you have an initial point and a intersection point, you could then go ahead and find that distance between the point and the line. That's basically kind of what we're doing here, except it's going to be in 3 space instead of 2 space, and we're not given a point and a line. We're given the equation of 2 lines. Now, if it were 2 lines in space, and I want to find the distance between those 2 lines, I can just find a point in one line, work with that, find a slope, and then work with the perpendicular slope and create a new line that will then, if it's in 2 space, automatically intersect the other line, and I can just really find, the distance here is the same as the distance here, assuming these are all perpendicular, which is the same as the distance here, and so on and so on. And I'll occasionally draw some 2-dimensional diagrams so we can have some kind of discussion on video, but we're going to be working with lines that are not parallel and do not intersect. We're going to be working with lines that are skew. There's only going to be one magic line that is going to be perpendicular to both given lines. Of course, and I'm highlighting this segment because the line's going to go on forever, but we're going to use those intersection points to then also do a little bonus expansion of finding the distance between those 2 lines. And that is what we're walking through in this video. I'm going to try and make sure you understand the process and not just seeing a solution that you can mimic and not know what the numbers really represent. And you'll see me looking at my iPad quite a bit. making sure that I don't make any small errors along the way, which carry through, honestly, a fairly long problem. So hopefully that helps and you enjoy the journey. So here we go. We need a vector that is basically a slope vector, a gradient vector, that we'll use to create line 3 that is perpendicular to line 1 and line 2. Well, remember in vector form, this is vector r, which is the position vector of any point on the line, is equal to vector a plus lambda times vector u or v or whatever name you're calling your position vector. So this is an initial point, and when I say initial point, I might interchange coordinate and of a point and the position vector. We're all talking about position vectors that go to the origin, start from the origin. So we have an initial point and a slope, basically a gradient vector. Now, of course, remember too, these vectors are not necessarily on these lines, they just have to be parallel because vectors are not defined by position, just their magnitude and direction. But we have a direction vector for line 1, which I'm going to call vector u. And we have a position vector for vector line 2, which I'm going to call vector v. And we're going to do the cross product between these two vectors, because if you have two vectors in 3 space and you want a third vector which is perpendicular to the given initial 2 vectors, you do the cross product. So we're going to find the cross product between vector v and u, and if you do this in reverse order, you'll just have a vector going in the opposite direction, which will still be, parallel, which will still be perpendicular to the 2 given lines. So that's going to be the determinant of vector I, j, k, just using those component vectors in the direction of the x, y, and z axis. Then for our second row, we've got negative 1, 1, and 2. For the third row, 2, 1, and 6. Taking out the first column and first row, we have vector, a 2 by 2 matrix of 1, 2, 1, 6. The determinant of that is going to become the component coefficient of vector I, and then minus, this is a positive, and then we go to minus. We're going to take out the second row, first column, and we have negative 1, 2, 2, 6. The determinant of that 2 by 2 matrix is going to become the coefficient of vector j, a scalar multiple of vector j, and then plus, taking out the third column and first row, we have negative 1, 1, 2, 1. The determinant of that will be our coefficient, scalar multiple of vector k. So we've got 1 times 6 is 6, minus 1 times 2 times vector I, minus negative 1 times 6 is negative 6, minus 2 times 2, which is 4, times vector j, plus negative 1 times 1 is negative 1, minus 2, vector k. Basically, our cross product in component form is going to be 6 minus 2, which is 4. Negative 6 minus 4 is negative 10, times negative 1 is 10. And then 1 minus 2 is negative 3. This vector, now I don't know if it's longer, the magnitude of this vector is longer than it takes to reach these 2 lines, or shorter, but this is going to be our, and I might go between, say, a normal vector or perpendicular vector. This vector is perpendicular to both of these lines, and so we have this, put this out of the way. Vector u crossed with vector v is equal to 4, 10, negative 3. Now I'm going to have to draw something in 2 space, but we are talking about skew vectors in 3 space. But there's a line here, and there's a line here. And we need to create a vector, which is going to be the direction vector for line 3. We need to create a vector, which I'm going to call PQ, that goes from line 1 to line 2. But now I'm kind of drawing this at an oblique angle. We talked about how we're going to use that line. That, first of all, that line has to be perpendicular to the 2 given lines, not oblique. So we need to create a new vector using a general point from line 1, because we don't know exactly where in space these lines are skew. So I can write, I can pick of lambdas 1, 2, 3, -5, 1.2, whatever I want, I can pick for lambda, and same with mu. But there is a specific point in space where those lines are going to be what? Perpendicular. We need a line that is perpendicular to, a new line that's perpendicular to these two given ones. So we need to remember that we have this, this normal vector, this perpendicular vector, whatever direction it may go from line 2 to 1 or vice versa. We need our new vector PQ to be parallel to our perpendicular vector. And how do you show that two vectors are parallel? You show that they're scalar multiples of each other. Well, we're just going to set them up to be scalar multiples of each other. So we need to realize that I'm going to write a position vector in component form, kind of in line with writing the vector form of this line in parametric form. A position vector for OP, any point along this line, is going to have an x component, which is going to be the original x is going to be, a new x is going to be equal to the original x plus -1 lambda. Our general y component is going to be 2 plus lambda, and our general z component is going to be 2 plus 2 lambda. And our general point q, position vector for coordinate q, a general point that's on this line, is going to be 1 plus 2 mu, 2 plus mu, and 4 plus 6 mu. So writing a vector PQ where its terminal minus initial is going to be 1 plus 2 mu minus terminal minus initial 1 minus lambda. Go to the x's, or y's, excuse me. 2 plus mu minus 2 plus lambda. And then z, 4 plus 6 mu minus 2 plus 2 lambda. So that is the general form of a vector that goes from line 1 to line 2. Now, that needs to be set up to be a scalar multiple of our perpendicular vector that we got from the cross product of 4, 10, and -3. Now, what's going on here is we're going to find, we have three variables in this system of equations. We have mu, lambda, and k. Well, normally if we have three unknowns, we're going to have three equations to solve those unknowns. Ultimately, through finding this solution of this three equation, three variable system, we're going to have a mu and lambda that we can use to then plug back into the general form of these coordinates to find an initial point for line 3. And we will also find k, which means we'll find out what is a scalar multiple to make the, sort of the, ultimately the magnitude of this vector equal the distance or the magnitude of this vector, vector PQ. So cleaning this up, we've got, I'm going to go back to white to make sure you can see this. We have 1 minus 1 is 0, so we have 2 mu. Negative times negative is plus lambda is going to be equal to 4k. And 2 minus 2 is 0, so we have mu minus lambda is equal to 10k. And then 4 minus 2 is 2. We have 6 mu. So 2 plus 6 mu. And then negative times positive is negative, so minus 2 lambda, and that's going to be equal to -3. Keep changing the size of my parentheses here. -3 k. So that is going to create, and that's going to be equal to basically PQ. So that is going to create our system of equations, which I don't think I'm going to have enough room to solve this with everything else up here, but I'll do this. We have 2 mu plus lambda is equal to 4k. We've got mu minus lambda is equal to 10k, and 2 plus 6 mu minus 2 lambda is equal to negative 3k. So I'm going to reorganize this so I have all the terms with variables on the left and any constants that we may have on the right. Get this work out of the way, give me some room to show you how to solve the system of equations, and give me a chance to make sure I didn't make some sign error or any other silliness here. Okay, so here we go. If this is a calculator-based question, and honestly it is, but I want to show you some how to work mechanically through solving a 3x3 basically system of linear equations, in case you need that. You can put this matrix as an augmented matrix into your calculator of 2, 1, negative 4, 0. Of course, in a graphing calculator, you have no option of having a vertical line there. 1, negative 1, negative 10, 0, and 6, negative 2, 3, and negative 2. If you put in this 3x4 matrix in your calculator under, say, maybe matrix A, of course, you'll be understanding that there's an implied vertical line here separating the variables the variable coefficients to the constants, and then do a reduced row echelon form, which is under the math menu of a graphing calculator for matrix math. You can have this answer pop right out. And the answer is going to be what the calculator will give you in the reduced row echelon form. That's where you worked with the Gaussian elimination process in Algebra 2 or Pre-Calc. You would get a matrix that is going to have a diagonal of 1s, and then the fourth column, which won't have an augmented line on it, is going to have the answers of negative 0.224, 0.254, and then negative 0.048. Yeah, so we're going to find these same numbers, but doing it a little bit of algebraic work, and this would be the values of mu that you could plug back into line 2 to find a general point there, or the value of lambda 0.254, yeah, that you could plug into this general coordinate of P to have that initial point that you could then use to write the equation of a line. But we're going to do this algebraically, or if this is perfectly fine, maybe you want to skip ahead a little bit. But we're going to find these values algebraically. So if you're not completely, or cannot be completely calculator dependent, or maybe at all dependent on how the numbers are worked out, what do I think is the quickest way to solve this system? You could write augmented matrix and do all those row operations and whatnot, but I think what I'm going to do instead is work on maybe getting rid of the reference of lambda first. And I'm going to pick that, no really good reason other than the fact that I already have a plus lambda and negative lambda. So I'm going to bring these first two equations through with addition, and that is going to create what? It's going to create 2 mu plus 1 mu is 3 mu. 1 lambda minus lambda 0. And we have negative 4k, and we're adding that with negative 10k, and getting negative 14k is equal to 0. And if I repeat that process with the second and third matrix, but we're going to need to do some kind of a manipulation here because we have a negative 2 lambda, and I want to get rid of the same variable as we do like a sort of a solving for systems by combination. I need this coefficient to be positive 2. So I'm going to multiply for my second step, which maybe I should color code that. I'm going to multiply this for my second step. I'm going to multiply this equation by negative 2, which is going to give me negative 2 mu. Negative 2 times negative 1 is positive, so I'm a plus 2 lambda. Negative 2 times negative 10 is 20, so plus 20k. and negative 2 times 0 is 0. And I'm adding these equations now. So I have negative 2 plus 6 is going to be 4 mu. I have 2 minus 2 lambda, which is 0, and 20k plus 3k is 23k is equal to negative 2. Now I want to take these two equations and combine them as well to get rid of a reference of one of the variables. Bringing these together, I want to get rid of the reference to mu. And I'm also going to eventually have to look at my work to get some of these answers. But multiply the first equation by, let's say, 4. And the second equation by, let's find mu first, because these are all already opposite signs. So let's multiply this by 3. Yeah, we're going to solve for k. Okay. And so we're going to multiply by negative 3. Yeah, we're going to leave let k alone. So we have 4 times 3 is 12 mu. 4 times negative 14, well, 4 times 10 is 40. 4 and 4 is 16, so that's going to be 40 and 16 is 56, so negative 56k. And then 4 times 0 is 0. And then coming down here, we have negative 3 times 4 is negative 12. And negative 3 times 23, well, it's going to be negative. 3 times 20 is 60, and 3 times 3 is 9, so negative 69k. And negative 3 times negative 2 is 6. And then we're going to add these orange equations, and we have 12 minus 12 is 0, so mu is gone. We have 50 and 60 is 110. Now we're at 116, and now we are at 116, and 9 is 125, so negative 125k is equal to 0 plus 6, which is equal to 6. And dividing both sides by negative 125, we get right off the top of my head, 6 divided by negative 125 is negative 0.048. And now we can just start back substituting that into our other equations to find out what the other variables are. Now you can use lambda and plug it into our general form for coordinate OP, or vector position vector OP, to get the coordinate of P, a coordinate that is on line 1. We can, if you want, plug mu into this form, of course, and we'll find a point that is on line 2. And then, well, let's write the equation of that line. So the equation of our line is equal to what? We need a point, and we already have the slope. So let's get all this off of here, because I'm looking around for space and trying to think at the same time, which is challenging for me. Now, as we close this up, I'm going to go ahead and give you the form of the other equation. Like, you don't have, when you write the equation of a line, you just need a point and a slope. I'm going to stick with my notes, find the general form of point P using lambda. Yes, and then I'll write out the answer for if you wanted to write the equation of that line and you found a coordinate that using line 2 to find that initial coordinate, that initial point that used to write the equation of a line. So we've got line 3 is going to be in the form of r sub 3 is equal to, okay, we need an initial point. To get a point from line 1, which is using lambda, we need to plug 0.256 into these equations. So it's going to be 1 minus 0.256, 2 plus 0.256, and then 2 plus 2 times 0.256. That's going to be that initial point for line 3 plus, let's call it beta, and use that perpendicular vector that we found way back, our normal vector perpendicular to vector to both lines of 4, 10, and negative 3. And this is going to simplify to be r sub 3 is equal to 4, 10, and negative 3. Now, we also said we're going to get a little bonus. We're going to determine the distance, the shortest distance that these 2 points or these 2 lines ever, get to each other. Which means that, well, we can do a couple of things. We can either find we have vector p, the position vector for coordinate p, and we can plug mu into here and find a position vector for coordinate q and do the magnitude of that vector, but we already had that scalar multiple, that k value of negative 0.048, and that was the scalar multiple that made the normal vector basically be equal to, right? We set the x, y, and z coordinates or components equal to each other. So we should just be able to, we are just able to say that negative 0.048, take that scalar multiple, apply it to this normal vector, get whatever that is, and then work out the magnitude, which I will show after I step off here and grab my calculator, because I kind of thought of this idea as I was writing up this problem. Also, I'll show that work, and I'll show the what the answer would be if you decided to find your perpendicular line using line 2 to give you that initial point. But for now, I'm Mr. True. Bam! Go do your homework.